You don't worry.
And just add them over.
Yeah, you just.
Because
So
even when
you know this.
second has, I would try to not have key.
That's when you
Oh,
want.
interesting.
Okay, let's start with number one, find the average value. The average value theorem. Go ahead and set up that formula. I'm doing f prime because it's asking for the average value of f prime, so. So a and b values are given to you, -4 and 4. So
-4 -4.
well, it's b minus a. So here's my a, that's my b value. So 4 minus -4 becomes positive. So think of this formula as rearranging the area formula for a rectangle. We know that width times height equals area. So height is equal to area divided by the width. So the 8 is kind of like your width component. And then your integral from -4 to 4 is your area component. If we understand that, then that's how we're going to get information from this graph. We're going to be pulling the area. However, we have to keep track of our positive and negative values. So regions above the x-axis, positive area or positive value. Regions below the x-axis, negative. So we're only looking at what's between the graph and the x-axis. So we see a bunch of shapes that we have geometric formulas for. So just a series of triangles and rectangles or squares, right? Okay, so triangle is 1/2 base times height. So 1/2, 1 times 1 is 1/2. This region is below the x-axis, so convert that to be a negative. Triangle also 1/2 base times height, positive. +1 for my square. And then triangle here, 1/2 base times height, 1/2. Here, this triangle, I think of this as a 1/2 base times height, so 1/2 2 times 1. So that's going to be a 1, but then below the x-axis, so -1. Half. Okay, any questions about how I'm getting those values and why I'm getting them? All right, so I'm just combine some like terms here. Out. +1. So 1 plus 1/2 plus 1/2 is going to be 2. So 2 is going to fill in for this definite interval from -4 to 4. So therefore, my average value is 1/8 times 2, which is 1/4. Okay, questions of one. Okay, number 2, find the average value of the function 4 minus x squared from 0 to 2. Same concept, but now instead of having to pull from a graph, we can just rely on definite integrals and power rule. Again, 1 over b minus a. I'm just going to jump directly to my a and b values. And then I can replace f of x with 4 minus x squared. I'll do that here. So I can apply power rule first. Remember, the bounds is never going to play a role with your depth integral initially, right? We got to go through the antiderivative process before the bounds can be involved. Right? So I'm just going to focus on that integral of 4 minus x squared. So power rule there. Now, if you choose to distribute the 1/2 through at the beginning, you can. I'm just going to wait till the end to deal with that 1/2. Okay, upper bound first. Minus big parentheses. Now lower bound. Gonna just zero out here. Okay, so 8 minus 8/3 gives me 16/3. But this only represents the area component, right? We still have to remember. Mhm.
Wait, why is 16 over 3 instead of like negative?
Instead of negative. So 8 minus 16 over 3 is 24 over 3 minus, sorry, 8 minus 8 over 3, which is 16.
Okay.
Right. So I'm not quite finished yet. There's still this 1/2 that we have to involve. So don't forget about your width components for your average value. So 16 over 6, which is 8 over 3. Any question with part A, finding average value? A part B says find the C value guaranteed by the average value theorem. So we know this is the Y value where the graph exists, but now we're just basically looking for the X value. So I'm just basically looking for the location of this order pair, and I'm just going to rely on the original function. I have the target Y value. Now I can just work backwards to solve for X. Take the square root. Plus or minus appears. So there's 2. C values, but we only care about the C value that lands either between or at the endpoint. So only the positive one makes sense. Questions so far? Okay, number 3. Whenever we see a problem just involving variables, we always want to ask ourselves, is this something that we can just do relying on power rule expansion? Because that's always our first option. Only if that option fails, then we want to consider U substitution. So we see numerator and denominator. That's not necessarily the issue. The issue is that there is more than one term inside that radical, separated by plus or minus. Now, if it was just 4th root of x squared, that's fine. You can just rely on power rule for that. But as soon as you introduce multiple terms inside the radical, or even multiple terms inside the part of your denominator, that's a little bit too complicated for power rule to handle. So power rule is out, expansion is out. We have to rely on or look to U substitution. Right, so we can rewrite this problem here with parentheses. Okay, so we want to consider a potential U value. What's our U value, you think?
That's for
Yeah, so we typically target what's inside the parentheses, just inside the parentheses. Okay, next unit, we may see some exceptions to this rule, but it's always a good place to start looking for your U value. Go through our derivative process. Find du dx, cross multiply. Solve for dx. All right, so I'm going to make my initial substitutions with my integrand here. So I'll replace what I underlined here with u. I'll replace the dx with du over 2x minus 4. Let's see where that leads us, because we still have this x minus 2 that is unresolved, but we'll deal with that a little bit later. So what still has to go away before we can consider a power rule or integration rules? Yeah, the x's have to go away. And this is not quite a clean reduction yet, but maybe I can do something with this 2x minus 4 to make it look more like this x minus 2. What can I do with this 2x minus 4? Yeah, factor out a 2. So if I factor out a 2, then I can make it 2 parentheses x minus 2. Now it's a nice clean match. Now I can take out. But there's still a what? 2, which I can pull out in front as what? 1/2. Okay, so this is where I'm at right now. Any questions so far? Right, so I'm looking to apply power rule. I'm definitely at a point where my expression is a lot easier to work with than what I began. But is there something that I still need to do before power rule? Yeah, I need that variable in the numerator, right? So if you think about power rule does not work if your variable is in the denominator. I have to force it to the numerator before it's ready. Okay, so push that denominator up, change the degree of the exponent to negative 1/4. Now we're ready. Now we can apply power rule. Okay, so add 1 to the exponent divided by that new exponent. Keep that 1/2 in front. (1/4 plus 4/4 is 3/4. Okay, do some cleanup here, bring that 3/4 up as 4/3. Okay, so I'm left with 4/6, which is 2/3. But is there anything I need to do to represent my final answer? Yeah, let's get this back in terms of x. So if you remind yourself that if you go through u substitution, your u is only a temporary variable. So at the very end, you want to bring back your original variable whenever you go through u substitution. Okay, so again, 4/6 is 2/3. And replace the u back in terms of x. All right, questions with 3. Okay, so number 4, whenever you see an absolute value function or integral with absolute value, I like to just go straight to, I mean, we can use power rule, but it's just a lot faster, a lot cleaner if you just think of it as, oh, I'm just finding the area of this region, which is going to look like 2 triangles. So the nice thing about the absolute value of x plus 3 is that it creates diagonal lines that are straight, so it turns out to be a nice, easy geometric shape. So first, let's graph this function here. Absolute value of x plus 3. That's just taking that vertex that was at 0, 0 and shifting it to the left 3 units. So we're going to extend from to -5 on the left and +2 on the right. I'm sorry. Because the absolute value of x plus 3, well, first off, absolute value of x looks like this, right? And then so absolute value of x plus 3 is going to take that graph and it's going to shift it to the left 3 units. Yeah. So anything inside the parentheses bracket is always going to go the opposite direction of what you would expect. So positive +3 means left 3. We know the graph is going to be a V-shaped graph. So I'm going to extend it as far as my boundaries go from -5 to 2. And if you look, we have 2 triangles that pop up, right? So really, this is the shape of the problem. And you're just asking, taking the definite integral. We know definite integral is area related. We can just add up the areas of these triangles. And normally we can't do that if these were, if this was a function that had curves, because if it did, we wouldn't, normally that doesn't fit a shape that we know the area for, but these we do. So we're going to take advantage of the fact that we know this looks like the shape that we have formulas for. Okay, so we know this graph is absolute value of x plus 3. So if I can find the height or the y values at these points, I also know the height of these triangles. So if I insert -5 into the function, what's -5 plus 3? -2, what's the absolute value of -2? 2. So my ordered pair is -5, 2. And 2 is the y value. It's also 2 units above the x-axis, which also represents your height. If I insert 2 into the function, 2 plus 3, 5. So order pair is 2, 5. And 5 also represents the height of your triangle. All right, so let's add up our areas here. Area is just 1/2 base times height, 1/2 base times height. And the base of my first triangle is 2. The height of my first triangle is also 2. The base of my second triangle is 5. And the height of my second triangle is also 5. So 1/2 base times height for the first triangle. 1/2 base times height for the second triangle. Okay, questions on the first page? All right, back page, number 5. So, we have to make sure that we understand the bounds are not the first thing we do, right? We got to take care of this antiderivative before the bounds can come into play. So I'll rewrite the problem without the bounds. Sorry, the next question we should ask is this possible with just power rule expansion? Can I expand my way through this problem? Okay, so anytime I have multiple terms inside a radical, it's stuck in that form. I can't distribute through. Now, if it was just one term inside, then yes, we can definitely just do some rearranging and clean that up. But as soon as we have multiple terms added or subtracted inside radical, we're kind of stuck. So we're stuck in this form. And if we rewrite using parentheses, we can spot our u value.
You just use the second calculus theorem.
We would do the second calculus theorem if it was asking for the derivative of this. If there was a find the derivative of this expression. Right? So anytime you're pairing a derivative and an integral next to each other, that's when you do second theorem.
Oh,
This is only asking for the integral. So
okay.
yeah, so second theorem is where you're undoing and doing the process of the same function. Okay, so we find our derivative, du dx equals -2x. We cross multiply. Make our substitutions. All right, so we need the x's to go away if we want to proceed, and the x's do go away, but we do just have to keep track of a -1/2 in front. Right, go through power rule. Do a little bit of cleanup. So now that I'm at this point, I have 2 ways I can go about this. I can either, I know I have to involve the bounds, but I don't want to involve the bounds at this point because this is in terms of u, but these bounds are in terms of what? In terms of x, right? So there's a mismatch of variables, and we don't want to go through that way. So either we bring this back in terms of x, then we can use these original bounds, or we convert these bounds to be in terms of u, and that way we can use this expression here. So either u with u or x with x, but we don't want to have x here and u here and try to expand that way. Okay, so I'm going to go through both methods here. I'll bring this back in terms of x first. Upper bound first. So 16. Think about the fact that cubing 16 is hard to do, but what if we made it smaller so we can deal with the square root, right? The 2 here. What's the square root of 16? 4. So negative 1/3 times 4 cubed. A lot easier to work with. 16 minus 7 is 9. 9 cubed is hard, but if I just think in terms of dealing with that 2 first, square root of 9 is 3, and 3 cubed is 27. Okay, the other method is converting the bounds. That means doing all of our calculations in terms of u. So that means I'm going to hold on to this negative 1/3 u to the 3/2, but I'm going to convert these bounds using that assigned equation that connects u and x. Push it through this so I can get these back in terms of u. Whatever starts as lower bound will stay as lower bound. Whatever starts as upper bound will stay as upper bound. So even if the values swap, it doesn't matter. Just put it where even if it flip flops, it's okay. So because, sorry. I've got these mixed up. Sorry. Root 7 is a lower bound. So because root 7 is a lower bound, I'm just going to take whatever number that I get in that spot. And up 0 was the upper bound. So whatever I had, whatever I convert is going to go in that space. And insert that 16 in. So we're back to where we were before. So 4 cubed, 3 cubed, same result. All right, number 6. All right, so we look at this and we see that there's no one rule that can handle this problem. I mean, we have a rule for sine, we have a rule for cosine, but we don't have a rule for cube root of cosine times sine. So anything that's more complicated than any one rule can handle, we got to think about use substitution.
Someone was asking me the other day, what's the difference between having the 1/3 outside the parentheses and then putting it before the x?
You mean,
Like cosine squared x.
okay,
Different. Yeah,
so cosine squared x is the same thing as saying cosine of x quantity squared.
okay, that's what I was thinking, but then when we take the u, we just take the u of the x, right?
We take the u for, the u is going to be the cosine of x.
Oh.
Yeah. Yeah, if you're going through u substitution, your u is never just x. That's a little too small, and after u substitution, your problem should look a lot different than what you started with. Yeah, so if you're going through u substitution, it's always more than just x. Okay, so we let our u value be what's inside the parentheses. Replace cosine with u. Sine is going to stay initially, and then replace dx with du over negative sine x. Push the negative out in front. Nice and clean power rule, a lot different than what we started with. Add 1 to the exponents, divide it by that exponent. This is indefinite integral, so we just have to clean this up and replace the u back in terms of x. All right, number 7, can I expand? So anytime I see x's in the problem and no trig, I always want to ask myself, can I rely on power rule? Can I expand this out? Can I distribute the x through? If this was just one term, I could, but anytime I have multiple terms inside, or order of operations, PEMDAS prevents this radical from being resolved. Well, we got to deal with this resolution before the x comes through. So we cannot distribute anything through multiple terms inside a radical. So this, we're stuck. We can't expand. We got to think about u substitution. Okay. All right, what's our u value? Or minus x. But is the degree favorable for things to work out nicely initially?
Yeah.
Okay, so the degree is not going to work out as nice as we would like. I mean, easier problems would be an x squared up here and x here, because then the degrees will match up and pair up. But we're still going down the right path. We just have to go through another set of substitution when we reach the next roadblock. So du dx equals -1. Solve for dx. Same thing as -1 du. Okay, make my substitution here. Right, the x's don't go away. We can't treat them separately and say power rule here and power rule here. We have to find a way to resolve that x. So what's available to help us with this x?
Yeah.
Yeah, we have this equation, which we can rearrange and get that x in terms of u. Then we have a clean substitution. So I'm just going to rearrange it. I'm going to push my negative use of 1/2 in front. I'm still not quite ready to do power rule, but at least I'm getting there. So if I simply distribute that negative u to 1/2 through, it should be in line for me to just apply power rule after the next step. So distribute this through here. Negative times negative is positive. I add exponents. 1/2 plus 1 is 3/2. All right. Go through power rule. Flip those fractions up to the top, but what's the final step I need to make? Bring back in terms of x, right? So use substitution. Keep reminding yourself it's only a temporary variable. It's not going to be in my final answer. I'm going to skip number 9. Really, you're just taking the antiderivative twice, and each time along the way, you're going to solve for c using the order pair from either the derivative order pair or from the function order pair. I want to do 2 problems that I have up on the board. I want to do an even-odd function, and also a definite integral with u substitution involving trig. So I'll put number 10 up here. Copy that. Okay, so the way that I approach these problems is I have steps up here on the board here. You want to apply and you want to build out your shorter interval first. Okay, don't look at the area value. Look at the interval. Pick out the shorter interval, which is what? Right, 4 to 0, right? But if I want to put this onto a graph, I like to read this graph from left to right because it's more straightforward. So what can I do to make this left to right? Flip the bounds, and then I got to change the sign. So it's not doesn't equal to 8 anymore. It's really equal to -8. So these mean the same thing, but this is easier to interpret. This is actually showing us, okay, it's going to be a region below the x-axis.
So in finding even and odd function, you always want to make sure it's going left to right.
That's right. Yeah. The integral from left to right, yes. Okay. So I know my region is below the x-axis. Now, as soon as I have this on my graph, I want to do something else before I reach my larger interval. I want to fill out the other side with the property that I know to be true. So if this is true, what I know about the other side of the graph, because the graph is also what? Yeah, symmetrical. So also -8. Right, so these are set in stone. We don't want to add to this, okay? So keep that in mind as we look at the larger interval. So that means from -4 to 8, I want all these regions to add up to be 12. So I don't want to be adding to this. It's already set. Only thing I have to play with is this region here. Okay. So what can I add to? So I have -16 here, right? So -16 plus what is going to be equal to 12? Let's test that out, right? So 28 minus 8 is 20, 20 minus 8 is 12. So we know this region must be 28 because we know that all these added up must be equal to 12. I'm sorry? Well, it's odd, so we'll do that for part B. Now, if this is 28, what do I know about the other side? Also 28, even, right? Symmetrical. So now that I have this in front of me, now I can worry about adding up the parts that they're asking me to add up from 0 to 8. I'm going to add up this part here. So the integral from 0 to 8 is equal to just 20, right? Okay, part B. Find the same region, but now let's assume that the function is odd. Hey, we're still playing with the same property here. So again, from 0 to 4, we want to create -8. But before I get to the larger interval, I want to fill out the property on the other side. If from 0 to 4 is -8, what do I know about the other side? Positive, because it's odd, right? So I'm going to have equal but opposite. So again, now I'm down to that last property. So I'm not going to change this. I'm not going to touch this. I just know that I'm going to add up and make sure that things total to be 12. So this is already 8. This is already -8. So what must be the missing piece? Positive what? 12. Right? 8 minus 8 is 0. 0 plus 12 is 12. So we get that to be true. And this is 12. What do you know about the other side? -12. So now that we have everything in front of us, we're going to total what they're asking for from 0 to 8 plus 12 minus 8. All right, one more thing I want to show you here. I have it up here on the board. Depth integral from 1 to 2, pi cosecant squared, pi over 6x dx. Okay, so first thing we do is understand that this is too complicated for any one rule to handle. We look for u substitution. What could be our u value? Pi x over 6. And I'm also going to rewrite this as well. I'm going to push that pi over 3 out in front. Exactly right. So pi over 6x is our u value. And so we find the derivative. I can push that pi over 6 in front. Understand that's just the coefficient. du dx equals pi over 6, cross multiply. Six du equals pi dx. Solve for dx equals 6 du over pi. Let's make our substitutions. There's no variables that need to be canceled out. We just have to push out all the coefficients. That just reduces to be 2, so we can just leave that alone. But it's really cosecant squared that we're focused on, right? Do we have a rule for cosecant squared? Cosecant squared is, we know the derivative of cotangent is negative cosecant squared. So therefore, the integral of cosecant squared is negative cotangent. So I'll merge that with the 2. Well, sorry, not 2 pi, just the 2, right? And not a plus c because we're dealing with depth integral. So now at this point, we can involve the bounds, but we don't want to use the bounds as we see it. This is in terms of u. These are in terms of x. I'm just going to bring this back in terms of x and resolve it. So -2 cotangent of pi over 6x. I'm going to evaluate my bounds now between 2 and 1. Upper bound first. I can do this now because this is in terms of x. My bounds are in terms of x. Okay, so 1 times pi over 6 is pi over 6. 1 times pi over 2 times pi over 6 is 2 pi over 6, which is pi over 3. Now we can't leave it in this form. We got to resolve it. So cotangent of pi over 6, if you think about your order pair at pi over 6 is √3 over 2, 1/2. Order pair of pi over 3 is 1/2, √3 over 2. Cotangent is x over y. So x over y is just √3 over 1. Cotangent of pi over 3, cotangent is just x over y. So my x is 1, my y is √3. My 2's cancel out. So make sure you know your unit circle values and make sure that you go one step beyond this at least. All right, so we can't have any trig hang out in our answer. Okay, I'll leave the rest of the time. See if you guys have any individual questions for me.
Yeah, it's just like, it's like.
I plug a 1 in. I have a 2 in for x.
Oh, yeah, the bounds.
Yeah. Right. So that over y is like 1. The y. So integral notation is area. So I just found the area as a triangle, so 1/2 base hand side, as a square, left side, base hand side. And this is a circle, so 1/2 square. My radius is anything below, I gotta make a line back as negative. Well, because eight minus eight. Zero plus one equals one. You always want to explore power, so let me show you some problems that is powerful.
For after value.
So it's not.
It's powerful because I can make my way through expansion of this. And also this one. I'm just separate everything and nothing that's going to be so that's power. Something that is just something would be this. Was similar. Was like the square root. Or I have. It's always more than one term in exam. More than one term. That's going to break down. If I can distribute through the area, any of these. Yeah. Even though it's like. Oh, no.
I actually did stuff.
I didn't study that.
Nope, I did.
Okay. Yeah.
So the derivative. The antiderivative.
Okay. No, that's been great. I had a question. It's not me. No, I think. Oh, yeah. Go back to.
Gotta be careful about that. So, yeah, no, once you start to see is the negative derivative. Most of the things that start with C is exponential so C can start with negative term, C can come with negative. These are the ones that, like, you have this in front of you, then cosine, sine, becomes the negative things, I'm going back, and the negative things has to be something.
Oh, it's not happy Friday.
What you gonna read?
Okay, so let's see this.
Is there a bound, way to go from C?
Okay, that's what it's like, yes. Give it a little teardrop.
Oh, I didn't go over second theorem.
Oh, yeah, do we need
We didn't know that one.
second?
Second fundamental theorem. No, over here. The second fundamental theorem. I'm sharing these two operations with each other. You can do two things. The function upper bound into the function. And then multiply by upper bound. Minus, this is a variable. I'm going to do the same thing here. Plug the lower bound into the function.
Oh, wait, so that's like your bag.
That's right. That's right.
You're young.
What if, so, wait, what if there's?
No.
It's not your boundaries.
You can swear.
Lower bound is constant. More this.
It doesn't have to be like that.
No.
And then, okay, then okay. Thank you.
No plus anymore. Thank you. This is not. I gotta put the balance to next tonight.
It's the actual, not a math one. 1 second, it's a test, and I got to media center, something for my next class. Okay.
I know, my report is 1, 5% is.
Through these problems where it asks you to find the guaranteed p-value, is what you get, a y, represent like the best.
Right.
Okay, and then you're solving, so this is like the x value, okay, so just put it in there.
It'd be original.
Thank you.
Your order here is. Think about this alphabetical order. Guys, I don't know your book Guys, all your book bags up front. Yeah, I'll leave that there.
I forget I love it. I don't know the terms of formula. We don't know that.
That's gay. Oh my God.
Seriously.
That's all.
Yeah.
Five, two.
That's the problem. Wait, is there concept of quiz on here?
Oh, I don't know.
Semicircles. Wait, beyond this.
First one, half.
That was not way where all these. No, it's, I already forgot. It's W. I wrote this. I don't know.
Yes. Like joules to pounds and stuff, of course, and I'm like, mathematically, incorrect.
I know.
No, I can't. Oh. I can get it with it. What's the cover?
Wait, right. Thank you.